Okay, today is the first lecture of the class about commutation and heaps of pieces. So we start with chapter 1, commutation, monoid, and heaps of pieces, the basic definition. So first section is commutation monoid. So I will start very gentle, at the elementary level. Everybody knows this identity. But maybe it's not true. No, in case AB and BA does not commute, then this identity should be this one. So we have some letters, A, B, C, D, letters, or formal variable. And some of this variable can commute, like AD equal DA, CD equal DC, or BC equal CB. And some pair maybe does not commute. And this is a graph, the graph of commutation of the graph of non-commutation. So see in green, it's a commutation of the variable, and in red, non-commutation. So in a binary relation like this, define you a graph, and a graph is a binary relation. And then I take a word, a monomial, in the variable A, B, C, D, like this one, W equal A, B, C, A, D. And then for this commutation rule, I am going to do some commutation of letters. You take two consecutive letters, like this one, BC, and then you apply the commutation rule BC equals CB, and you get another word, A, CB, AD. Then I can repeat in other place, in other word, AD equal DA, so I get another word by commuting these two consecutive variables. Now I can commute C and D, CD equal DC, you get this word. Also, if I go back here and A and D, I can commute them, and I get DA. I can again try, for example, here, CB is going to be equal to BC, and I get back this word. Now, if you try to do other commutation, it's finished. I have done all possible commutation in all this word, and I get a class of words. I get an equivalence class of word, equivalence for the congruence generated by this commutation relation. And these classes are going to form a monoid, algebraic structure, and this was the topics of the Cartier-Foata lecture note in '69. They introduced what is called sometimes the commutation monoid with some partial commutation of the letters of the formal variable. So this monography is in French, but it has been republished in the Séminaire Lotharingien de Combinatoire. It's a journal. It's a seminar in Europe twice a year, and it's also a journal, which is electronic journal. This is the website of the journal. And if you go to the homepage, you click on book, and you will get the Cartier-Foata monography retyped in tech. And what is interesting for you for this course is there is an appendix by Christian Kratenthaler, which is written in English, and which gives the main definition and two of the basic lemma and an example of this theory of heaps of pieces, which is related to commutation monoid. So Cartier-Foata, here is a picture of Cartier in Max Planck Institute showing a formula. This is a Grothendieck formula. I don't understand anything of this formula, but it's you can look at it as a piece of art. This is Foata in a lecture, and you see in his hand, he's taking the infinite in l'infini dans la paume de la main, like there is this famous poetry about the universe, and you see the bijection. There will be many bijections in this class. It's a bijective-oriented course. So monoid, elementary definition, a monoid is you have a product, a law which is associative. UVW equal to UVW, just associativity and a neutral element or unit element. So it's a very weak structure. If you have inverse, then you get group theory, which is very rich, but monoid is a very weak structure. We don't necessarily have some inverse. So very elementary example, the positive integer with addition or product are monoid. There is no inverse in this monoid. And in this course, we will use many times also the free monoid. The free monoid is generated by set A. So you have an alphabet. The free monoid is a set of all the words. So it's a sequence of letters. All the words A1, A2, AP. And the product of two words in this monoid is just a concatenation of two words. You put them together. U multiplied by V. This is the product, which is associative, and it's very natural. In any language, you put the letters from a concatenation of letters, and the empty word, no letters at all, it's the unit element. And the length of the word is the number of letters. So here the length is P, and the length of the empty word is 0. Or the free monoid. Now I go back to my commutation relation. So I have a binary relation, the partial which defines the commutation relation. So it's a binary relation which is anti-reflexive and symmetric. What does it mean? Symmetric, if you have A and B are relation in C, then it's equivalent to say that B and C are in relation. And anti-reflexive means that A is not in relation with A. It's maybe strange to say that A does not commute with A, but that's the rule. I need this rule in this course. In fact, it's not necessary to commute A with itself, so you forbid the commutation of A with itself. And then I define this symbol to be the congruence generated by this commutation relation. So two words will be congruent, equivalent, if and only if you can go from one word to the other word by doing this commutation of adjacent letters according to the relation C. So we have seen before a class of 5 words which are all the word equivalent for this equivalence relation with some commutation relation. So the commutation monoid, by definition, is the quotient of this monoid by the congruence generated by C. In a more precise way to see the product. So you take, I will denote in between brackets the equivalence class of a word. So all the words equivalent to W by doing commutation of adjacent letters. And the product of two classes. If I take the class of the word U, multiplied by the class of the word V, it's just the class of the word UV. And this product is independent, you can see this trivially, it's independent of the choice of the representant U and V of the class. So two particular cases of this, two extreme cases of this commutation monoid is if nobody commute, then you have the free monoid. And if any pair of letters AB distinct commute, then you have the free abelian monoid, which can be written, it's like this monomial, that's the generator of the free abelian monoid, generated by the alphabet A, where X1, X2, Xk are some letters of the alphabet. So between these two extreme cases, nobody commute, everybody commute, you have between them commutation monoid, which also are sometimes called the free partially commutative monoid. It's a free structure for the commutation. So we are between the free monoid and the free abelian monoid. So there is many, many things to say about this algebraic structure. And sometimes these monoids are called also the trace monoid. So a trace is an element, it's just a class of words. And it's called trace in the with computer science. In computer scientists call this a trace monoid because it's a model for parallelism. Each letter is a symbol of a certain action. You are performing something, an operator or a certain action. And if the two letters commute, then you can make the two actions in parallel at the same time. But if they don't commute, it means that if you do the action A and then the action B, the result will be different to do first a B and then A. So it's a theoretical model. It's a modelization of parallelism, or when you have concurrency access to data structure, A and B at the same time want to get to go to certain data. So this trace monoid, in fact, was introduced by a computer scientist, Polish computer scientist Mazurkiewicz in 1977. He was working with what is called Petri nets and a model for the logical behavior of safe Petri nets. So it's we are inside theoretical computer science, and many work have been done in theoretical computer science about this trace monoid. You know, the free monoids, it's a subset of language, there is automata, algebraic language, all this. So there is a modelization using this trace monoid, which appear to be the same as a commutation monoid. And even there is a book, the book of trace in 1995 about all this. This is a computer science point of view about commutation monoid. So the commutation monoid was introduced by Cartier-Foata. In fact, it was an algebraization of something introduced by Foata with, in his thesis, with rearrangement of sequences. And this thesis was a combinatorial point of view of some probabilistic theorem, Speyer-Andersen theorem. So there was some probabilistic theorem. Foata put it in the combinatorial way. Then Cartier came and put it in the algebraico-combinatorial way. And then the speaker came in 1985 and put it in a geometric way, so with heaps of pieces. So heaps of pieces is again a reinterpretation of the commutation class in terms of the intuition when you put pieces one over another, as we will see. So definition and example, elementary definition. So what is intuition between heaps of pieces? This is a picture of a heaps of diamonds on a chessboard. So the idea is you put pieces like this, diamonds. Suppose you have diamonds in wood. Each diamond can project on the ground, on the chessboard. The projection will be a union of two cells, two consecutive cells, a black and a white cell, which can be horizontal or vertical, or vertical. It can be in the two directions. It can be, the projection can be like this, or it can be like this. So suppose you put your diamonds fall down on the chessboard. Each time you choose the diamonds high above the heaps, then the position of the diamonds will be two consecutive cells, and the diamond maybe fall down on the floor, maybe fall down on what we have done before on the heap. And the intuition behind heap is, the heap is what you see when you have when you forget in which order you put the diamonds. For example, if I take these diamonds here, from the picture, I can say that this diamond was was putting after this one. But between this one and this one, I don't know which one fall down on the floor before. So another example, it's you see you have diamonds in each column here. Each column is labeled sigma 0, sigma 1, sigma 2, sigma 3, and here the diamonds are falling down, and what you see is the heaps. And here you have a word, which means the first diamond which fall down was in the column sigma 2, second diamond was in the column sigma 3, etc. So if I just repeat it, you see the first diamond which fall down is sigma 2, then the second diamond in sigma 3, then sigma 5, then sigma 1, then sigma 4, etc. So when you have a word like this, you get a heaps of diamonds. You forget in which order. You forget the word, but you keep some information by looking the heap. So this is the intuitive intuition behind heap. This is not a heap. It's like a game, you know, the Mikado game, when you have some sticks, you put them on the table, and then the game is you have to take off the sticks one by one without moving the other sticks. So here you will not be able to take off these pieces one by one. So here is the intuition. Now is the formal definition, the mathematical definition. There is different definition. I will give the first definition. In the next lecture, there will be another definition, equivalent definition, but one possible definition is this one. So heap, you have a set, P. P is a set of basic pieces. Right, it's a certain set. In my example, was the dimers on the floor, 2 consecutive cells of the chessboard. Now we have a binary relation on the set of basic pieces, which is symmetric and reflexive. So if A and B are in the, I call this dependency relation. If A and B are in dependency, then B and A are also in dependency, and A is in dependency with itself. I put a C because it's in French, it's concurrent. It's like competition in English. Concurrency is not the same as concurrent. The C bolt was, because the French name, I keep the same notation. In English, it would be dependency or competition. So if you remember data structures in computer science, there is some competition between 2 operators. So this is axiomatic of this non-parallelism of the action in computer science. So you have these 2 things, a set P, binary relation, then a heap, capital E, is a finite set of pairs. So we have some pair alpha I, where alpha is a basic piece. It's an element of P. So I call alpha the projection of the pair alpha I. And I is a level of this element. So the pair alpha I will call these pieces. Piece like the dimers on the heaps of dimers on the chessboard. So pieces are element of the heap. And the projection is basic pieces. And you see the level correspond to, I give you 2 pictures of heaps. The level corresponds at the height of the dimer. You have suppose the dimer are in wood and with the same width for everybody. And now the definition, there is 2 conditions, 1 and 2, which translate the intuitive idea of these heaps of pieces. So condition 1 and 2. So condition 1, if you have 2 elements of the heap, alpha I and beta j, such that the projection are related by the relation of dependency relation, then I is different of j. And intuitively, you cannot have 2 pieces at the same level such that they are independent of each other. If you think of the dimers in wood, they would overlap each other. It's solid pieces in wood, and they cannot overlap when they are at the same level. Second condition is if you have a certain piece at a level non-zero, 0 level, I will call this the floor. If your pieces is a certain level high, then there exists another element of the heap. There exists another piece, beta I minus 1. So it's a piece, an element at the level just below the level I. There is somebody at level I minus 1, such that the projection, alpha and beta, are independent. They are related by the relation, the competition relation. So intuitively, with your dimers in wood, it means that the dimer at level I is relying on somebody which is supporting somebody just below, is touching another dimer that's below I minus 1. So these 2 conditions give you a formalization of this intuitive idea of heaps of pieces. So first example, a heap of segment on the integer. So the basic piece are all the segment AB. So which means all the integer between A and B, including an A and B. And the dependency relation, 2 segments will be dependent if and only if they have a non-empty intersection. So here is an example of a heaps of segments. So let's check the 2 conditions, 1 and 2, of heaps of pieces. So condition 1 means that if two segments are at the same level, like this one, then the intersection is empty. So they cannot overlap. Two segments at the same level cannot overlap. So your picture is a set of segments on the square lattice, which are all 2 by 2 disjoint. Now the second condition tell you like this. Here is a segment at level 4, and this segment at level 4. So there must be somebody, another segment at level 3, like this one, such that the projection, here are in blue and green are the two projectional segments. The projection must be related by the relation of dependency, which means they must intersect. So here is an example of a heap of segments. The particular case of heaps of segments are heaps of dimers. So each segment is only 2 points. It's a two consecutive basic piece are consecutive point I plus 1. And again, I have a heaps of dimer means that all the dimer you have a disjoint are disjoint in the square lattice. And if you have a dimer at level I, there is another dimer at level I minus 1, such that if this dimer is I plus 1, if this one is J plus 1, then the distance between I and J is less or equal to 2. Another example is subset, non-empty subset of a set. So you take a set capital X, you take a certain set of subset, the basic piece, and the dependency relation is two subsets are dependent if and only if they have a non-intersection, non-empty intersection. In fact, we will see in further lectures, there is an exercise that any heap can be viewed isomorphic in a certain way. I will define isomorphism, can be viewed as isomorphic to a heaps of subset. So example here, you see it's what are my basic piece? It's a union of two consecutive cells of the chessboard, but take the interior of the union. So that if the two, so that for example, this basic piece is not dependent of this basic piece. The intersection is empty if I take the interior of the and so here is an example of heaps of subset. Another example, which will be very useful in physics, it's a heaps of hexagon. So I am taking the triangular lattice, and an hexagon is a union of like this, a union of 6 triangles. So here are 2 by 2 disjoint hexagon. So the dependency relation is again intersection is non-empty. And here is on this lattice. So here is a heaps of hexagon. They fall down one by one. And at the end, I will forget in which order they fall down. So okay, what I get, you see, is a pyramid of hexagon. Pyramid means we will meet many such heaps in the course. Pyramid, that means that if you look above the heap, all the hexagon, you don't see them in full size. You don't see the 6 triangles. There is only one hexagon that you see in full size. So this will be a very important class of heaps, the pyramid. And so here is a pyramid of hexagon. And we will see in the part section related to statistical mechanics that there is some gas model, and there is a thermodynamical function in the gas model, the density of the gas, and the density of this gas will be exactly up to the sign. It will be the generating function of such pyramid of hexagon. Generating function means you are going to enumerate. It's a formal power series. The coefficient of t power n is the number of pyramids of hexagon you can make with n hexagon.
What is t?
T is a formal variable. In thermodynamical, T will be in physics the activity of the gas. Well, chemical potential, activity of the gas. In cohesion, it will be the formal variable. T is a certain variable in thermodynamic. And it will be, this function can be put in formal power series. And this formal power series, the coefficient of t power n will be an integer, which is not obvious. And this integer will be exactly the number of pyramid of hexagon with n hexagon. Up to translation on the hexagonal lattice, there is no bound on the hexagon. So with one hexagon, there is 1. With 2 hexagons, there is 7. With 3 hexagons, I think there is 42, but I don't remember. And the very amazing fact is that this generating function is an algebraic generating function. And there is no combinatorial explanation of this fact. So you see, heaps, enumeration of heaps can be very hard, very difficult problem. So let's go back to elementary things on heaps. So say I have some discrete hexagon. Here hexagon are 6 points. Now I am on the hexagonal lattice instead of being on the triangular lattice. But you feel immediately that taking heaps of such discrete hexagon with a concurrency relation is that 2 hexagons will intersect, maybe with 2 points, or maybe with 6 points. So taking heaps of this, or pyramid of this, is the same, is isomorphic to taking heaps of hexagon in wood, where it was a basic piece, but just a subset. It was 6 triangle of the plane of a real number. So another example, which we meet many times in this class, especially when we will go to linear algebra and a connection between all this and classical theorem in linear algebra, when we'll do walks, paths, etc. There is many useful connection which involve heaps of cycle. So a cycle, what is a cycle? Here I have an example of basic piece cycle on a certain set. Here I take the integer z. So a cycle, it's it's on graph theory. Maybe they don't use this term cycle. Cycle will be the same as cycle of a permutation. So it's a sequence of elements or vertices, which are all distinct. When I turn around this, all distinct vertices and up to a circular permutation. You don't say what is the starting point of following this cycle. Just think of the permutation written as a union of cycle, of disjoint cycle. And the support of the cycle will be the underlying set of vertices. And again, the dependency relation is 2 cycles are dependent, if and only if their underlying support are disjoint. So you see, I can take heaps. Here I have heaps of subset, but on each subset there is a certain combinatorial structure. Each subset there is vertices, and I put a cycle on this subset. So here we will meet, especially in chapter 3, chapter 4, there will be many heaps of cycle. So here is the evolution of the heaps of cycle. And this is the most general case. You see, imagine, what is heaps? You have a graph. Below, you have a dependency graph. So the green edges are the edges of the dependency relation. So 2 of these vertex are in dependence. And above each vertex, you see, I have some like a fiber, like a vertical line. And each of these lines, I have big red ball, which are the element of the heap. And so each pile of ball, they project on the graph, on the vertices. And now the condition to have a heap is that when you have if 2 balls like this one, these 2 balls, they project on 2 vertices which are independent, which means the ball, if you make the ball, you lift the ball moving the ball on the vertical line, they are going to collide. So suppose the balls are big enough to be bigger than half of the length of the edge of the 2 vertices on the projection. You cannot, these 2 balls here, you cannot move them so that one of them is going to pass the other one. But these 2, this one and this one, then there is no obstacle to move them above or below. So this is a general image of a heap. You see, it's a graph theory. It's embedded in graph theory, but with something more above it. This is the whole structure of ball or vertices. You can pile them one over another. So now on these heaps, I'm going to define a monoid, a heap structure, a heap monoid. I can define the product of two heaps. Intuitively, it's to put one heap over another one and everybody fall down. So the one possible mathematical definition is the following. I define a pre-heap. Pre-heap is exactly the same as heap, except you have only the condition one. Only condition one that so you have basic piece, you have the dependency relation, you have the poset E, only condition one. So this is an example of a pre-heap of segment, which means they are floating in the air. You see, this segment, there is nobody below it at level I minus 1. So I can make elementary move. Alpha I minus 1, or the level I plus 1. You move it by one level up or down, if possible, which means you make the move without violating the condition 1. Example on this heaps of segment. See, I can put this segment one level down like this, or I can put this segment one level above, you see. So these are elementary move in my heaps, in my pre-heap. So I have an equivalence relation. All the pre-heap I can generate by doing this elementary move. And intuitively, it's obvious that in each equivalence class for this elementary move in a pre-heap, there exists a unique heap equivalent to your pre-heap.
So what is equivalence?
The equivalence is doing the elementary moving like this. So this, if you take a heap, if you can do the elementary move, then you get another heap equivalent, and the equivalent is the equivalent generated by a succession of such elementary move. Can go up, down, so I denote this equivalence relation by this. So I have a whole family of pre-heap I can generate from one of the pre-heap, and I claim that in this family, in this equivalence class, there is only a unique heap, I denote like this, in the equivalence class of pre-heap. So example here is all the possible pre-heap, and what is the unique heap? Intuitively, you make the gravity working, and intuitively each segment is 1 centimeter wide, and so they are going to fall down by discrete level 0, level 1, level 2. So look here, it's from the pre-heap, like this. I have a unique heap. Intuitively, everybody fall down. But you immediately think that why to do the gravity? Maybe I can do the anti-gravity. So if you put some gas inside each diamond, and they will go to the ceiling. So also there is a unique, like something like anti-heap, the reverse condition. But maybe you can still keep the pre-heap in the idea. Yes? Does it depend on what? On the...
If you perform some moves first, you may be prohibited to do the second move of another one.
No, only...
Heap will be the same.
Heap are the same. But if you, in the movement, if two pieces going to collide, then this is not allowed. You must have the condition 1. Condition 1 means that if two elements are the same level, then they are not independent. They are not in the relation C script.
Here there are 1, 2, 3, 4, 5, 6 pieces are there.
Yes.
And if I decided to move that piece 1 first and piece 2 first, and there are different possibilities.
No, it does not depend of the sequence of movement. When they fall down, yes, this will be a theorem on heaps that. Okay, so now the heap monoid is defined in the following way. product of two heap E and F. So start from the red heap, like this, heaps of segment, and take a second heap, F in blue. So the two heaps, you see, if you put them, the two pictures together, they overlap. But to take the product, just take the blue segment, the blue heap, and as a pre-heap, in the equivalence class, put it high above the red one at a level so that the level of all the blue pieces are bigger than the level of all the red pieces. So you do elementary move to get a pre-heap, a blue pre-heap. So now I take the union of the two. The union of the blue and the red is a pre-heap. As soon as the blue segment are at a level above all the level of the red pieces, so both of them are pre-heap. The union is a pre-heap. And now you take the unique heap in the equivalence class of this pre-heap, which give you this heap. The blue pieces, intuitively, they are falling down on the red pieces. It does not depend on the order in which they fall down or the movement. The result is always the same. So this is very intuitive. It's maybe difficult to formalize all this elementary fact by intuition. So it is a picture which formalizes the picture underlying the formalization of the product. So we have a heap E, a heap F. The product of the two is you have to take the heap E. T of F is a translation. You translate F high above the red one, but at a level very high. And then you take the union of the two, which is a pre-heap. And then you take the unique heap in the equivalence class. And no, it's not commutative. Because if you have this species multiplied by this, and this species multiplied by this one, it's not the same as this species multiplied by this. As soon as the two subsets intersect, this is independent. So just take any inverse. It's a monoid. There is no inverse. If you want to do inverse, it's possible, but then you have to put blue dimers, red dimers, and the blue and the red is going to, on the same position, are going to cancel and evaporate. They will cancel it. So it's possible to put inverse. But this is another story.
We have to introduce a new concept like
yes. Some concept. We will see at the third part with the temporally labeled algebra. We will see some that there is some cancellation. Some if you put the square is one, or the square is equal to itself. So it's possible to do some more relation.
Yeah. So then there's simple substitution in the generic.
Mm-hmm. So there is some more. The braid. I will at the end of the class. I will give you some more structures, the symmetry group, temporally labeled algebra, all this. There is more relation than just commutation relation. Well, there is many.
It's like in groups we have like the elements who commute with one element like that. Heaps with us we have the collection of heaps commute with this some properties of that kind of.
Well, there is some property. You will see in the class, in the course. Many class of heaps. Certain class will appear, and there is some interesting property or some basic lemma, everything. So you will see. Just wait for the other lecture. So I come back now. I have two monoids, the commutation monoid and the heaps monoid. I claim that they are equivalent, that the idea of heaps is equivalent to the idea of a commutation class. So there is an equivalence, an isomorphism between the two heaps. Every heaps monoid is isomorphic to a commutation monoid. So here is a relation. You take basic pieces P, and for any word, I take the free monoid generated by P, the set of basic pieces. So my alphabet for the free monoid is P. And if I take any word as a sequence of consecutive basic piece. Then I can define a heap, which is a product of each of this elementary heap. This symbol means the product of heap, and each basic piece is viewed as a heap. It's a heaps, which is a single pieces at level 0. I will identify a basic piece with a certain heap having only one element. And to each word, I can take the product of all this one element heap, and I get a heap. So I have a map from the free monoid generated by the basic piece to the monoid, heaps of monoid with basic piece P and dependency relation C script. So example, take your basic piece alpha, beta, gamma, delta as to being subset of set. So my set is 3 elements, x, y, z. I take 4 non-empty subset, x, y, y, z, x, and delta equal, no, it's not, delta is z. And this is a dependency relation. Alpha is, and beta have an intersection, non-empty intersection is y. Alpha and gamma has a non-empty intersection. Alpha and and gamma, yes, has a non-empty intersection, which is x, and beta delta has a non-empty intersection, which is y. No, which is z. The delta is z. No constraint at all. So you take a word alpha, beta, gamma, alpha, delta. And to this word, I can take the product of each letter considered as a heap. So I take first alpha, which is a subset xy, then multiply as a heap by beta. So beta is yz.
But also you have alpha, beta.
Yes. This is yes. Dependency relation. Any letters is in dependency with itself. So I should put the relation. Here I only put the relation with different letters, distinct letters, alpha, beta, gamma, delta. But of course, alpha is in relation with alpha, beta in relation with beta, gamma in relation with gamma. So here, alpha, beta. Now I multiply by gamma. So gamma is a subset reduced to x. I multiply again by alpha. So another dimers, alpha, xy, is falling down. And I multiply by delta. And what I get, you see, is heaps of pieces of single point or dimers, which is a heap associated to this word. But different word in the same different word can give the same heap. So if you take all the word associated to this heap, giving this heap, here are there is 5 possible words which give the same heap. And you can see that these 5 different words are exactly the 5 words I get just at the beginning, starting with this word, A, B, C, A, D. So I have these 5 words in the equivalence class, exactly the same as this one, as soon as replace A by alpha, B by beta, etc. And as soon as now I take the commutation rule, commutation relation, to be exactly the complementary of the dependency relation. So commutation now for 2 subsets means that the 2 subsets are disjoint. This is a commutation. Dependency means the 2 subsets have a non-empty intersection. And you can check that these 5 words are exactly the word you get, the same heap like this. So now I have my fundamental lemma. I have this map sending the free monoid onto the heap. I take the commutation relation to be the complementary of the dependency relation. And I have lemma 1. If 2 words of the free monoid generated by basic piece are in the equivalence relation for the commutation of letters, then they give the same heap. So lemma 1 is obvious. Just think of when the pieces fall down. If you take 2 consecutive pieces falling down, if you commute them, and if they are not dependent, then it will give the same heap. You can making falling down together. So this is a concurrence. This is a parallelism in computer science. The 2 pieces can fall together. Now, lemma 2, the reverse, is that if two words of the free monoid P star give the same heap, then they are equivalent for the commutation relation. And proof in the next section, which will be the next lecture. I need to prove this, the so-called Cartier-Foata normal form of a class, of a word, and I will need, or this is not totally obvious to prove the reverse. So from these two lemma, which the proof will be given in the next lecture, from these two lemma, I can state the following definition. So definition, I define the map phi bar is a unique map making this diagram commutative. You see, if two words, if I take an equivalence class, then the phi bar of the equivalence class of U is defined as to be phi of U, and this map does not depend, this phi of U does not depend of the choice of the representant because of lemma 2. So lemma 1 and lemma 2 give you, enable you to define this map phi bar, which is going to be a map from the commutation monoid to the heap monoid. And proposition, this map is an isomorphism of monoid. So I can say the heap monoid is isomorphic to the commutation monoid. And then the relation, again, is a commutation relation, is a complementary. So you see now why a letter does not commute with itself, because a letter is deeply dependent of itself. If you think of the pieces following one another, or heaps of subset, this is the worst case, where the A is the intersection A and B, when A equal B is the maximum possible intersection you get. So they are deeply dependent, two pieces, one over another, A equal A. So other example of heaps of dimers, this will be important in the many application and connection with pure mathematics. So if I have heaps of dimers, it was a subset I plus 1. Now if I denote the dimers to be sigma I, so the commutation relation is just two dimers commute, or two letters sigma I and sigma j commute, if and only if the difference between the two index, the distance between I and j is bigger or equal to 2. So example, take this word sigma 1, sigma 2, each dimer I plus 1, and then to sigma 1, sigma 2, sigma 4, sigma 1, sigma 4, sigma 3, sigma 0, sigma 4. From this word, you get a heap. Now the lemma 2 tells you that these two words in red and blue, they are equivalent for the commutation relation. And this commutation is, you met him in many, the symmetry groups, the braid groups, the K algebra, temporary group. There's many algebraic structure having this commutation relation. So let's check that the two heap, the blue heap and the red heap, coming from the blue and red word, you are going to see they give the same heap. And I claim you can go from one word to another by this elementary commutation. And this heap, so, is a representation of this relation. You see this first relation, the braid group, Bn, the symmetry group, and the temporally algebra, all of them have generator, and this commutation relation is the first relation. Of course, there is more relation. So there is some relation on the heap, but the first representation of when you have only this single relation is heaps of dimer. It can be useful, and we will have a whole chapter on temporally algebra, where the generator of the temporally algebra, you can see easily with heaps of pieces, heaps of dimers. We will do these two other relations, and you will see from heaps, it will be easy consequence that the dimension of this algebra is the Catalan number. The very classical Catalan number, the number of Dicpas, the number of binary trees, the number of triangulations, many things are enumerated by Catalan number. So this was just an introduction to the course. Here I give you content of the course, but before last year I gave a class an introduction to enumerative algebraic and bijective combinatorics. So this was just an introduction last year. So this class is following the first class, but you don't need to follow the first class. It's independent. You can follow this course independently of the first course. So there will be some overlap. Like, for example, I will need a generating function. I will need Catalan number. I will need some few combinatorics, especially a power series generating function. So I will repeat some part of this class of last year, but the philosophy is the same. The philosophy is to do as much as possible bijective proof to replace analytic calculus, to replace calculus by some correspondence, some bijection. So this is the philosophy, the spirit of the course. And now I give the content of the course. Yes, a question?
Once we have a two heap, is there any natural morphism between them?
Natural what? With two heap, yes. Is there any natural?
I mean, sets we have bijection, and then we have continuous function in different setups.
Well, there will.
Category. So, what will be the natural morphism comes here?
The natural, I don't understand very well the question. What is natural?
Means once we have a topology, the continuous function is the natural one. If you don't have the topology, the set the bijection is the natural one. So like once we have two heaps, one heap here and the second heap here. What is there any?
You mean you have two heaps or you have two commutation monoids?
So there is some, between different heaps, monoids, there is some relation.
Okay.
We'll see some, because some heaps we'll do, for example, heaps of cycle, and then we'll cut the edges and have another heap. The two heap will be isomorphic, or there will be some morphism from one heap's monoid to another heap's monoid. There will be many construction, many bijection, many construction, or inside. So the whole course will be, you will see many different construction.
Make more variables commute and then the
Yes.
will shrink.
Mm-hmm.
One will map onto the other.
Mm-hmm. Yes, you can change one heap. There will be some operation on heaps, like derivative. I will do derivative. I will do substitution of a heap into another heap. So there will be some operation on heaps which reflect some operation on formal power series, which reflects some operation of analysis. So there will be. I will do the derivative of a heap. There will be one of the fundamental lemma will be the logarithm of a heap. I will take the logarithm of a heap, and I will take the derivative, and this will give you pyramids. So pyramids, I have shown a pyramid of hexagon. So this will come from an operation, which is a logarithmic lemma. And in physics, when you have the partition function, you take the logarithm, you get the density. So it's exactly the same, similar operation. And this will prove theorem from physics to give an interpretation by taking, defining the logarithm of heaps, the derivative. All this is possible. So I give you the contents of the course. So the content of the course is, so the course will, the first lecture will be about three basic lemma. The first basic lemma will be an inversion lemma, which tell you the generating function for heap will be, so for the general generating function will be the inverse of a certain generating function of trivial heaps. And the generating function will be the ratio in general of two, a numerator and denominator. Now a second lemma will be that the logarithm of heaps will be related to pyramids, having only one piece you can see in full size. And the third lemma will be that any path, all mathematics, there is path in probability, random walks, or in physics, a walk, a path, or in a graph. So a path is equivalent to make a heap of cycle with some condition on the top of the heap. So this will be very useful, these three basic lemma. And then there will be some basic definition in the theorem. So we'll see commutation monoid in the in this lecture, generating function for heaps, and so this is the first part of the class. This is the basic, all the basic theorem and the basic lemma. Now the third part will be application to classical mathematics. So will be a strong connection with linear algebra. 30 or 40 years ago, a lot of combinatorics, they tried to reprove all the classical theorem of linear algebra, Hamilton theorem, Jacobi theorem, etc. We prove them by only combinatorics. And you will see the heaps of pieces is a unification of all this combinatorial proof. And there will be the famous McMahon-Master theorem in this. So there will be, there is a strong relation between heaps and continuous fraction. And also strong, we'll do some algebraic graph theory, the chromatic polynomial, a cyclic orientation, all this will be able to do, or reprove some classical theorem using heaps of pieces. So it's a unification of different proofs which have the same hat. Everybody has the same hat with the heaps of pieces. So there is some application to theoretical physics or connection. for example, the directed animal problem in some gas model can be completely solved using a connection with Heaps of Pieces. There was some work in what is called quantum gravity. It's a unification of relativity, general relativity in quantum mechanics. So there is different theories. There is a string theory, there are other theory, and Lorentzian triangulation. There is some physicists working on this. This is a discretization of the space-time, but in 2 dimensions only, there is explicit formula, and this explicit formula, the Catalan number appear, and it's explained very easily with a connection with the heap. Also some solid and solid model in physics, enumeration of polyomino by area. The QBSL function appear, and there is a very natural explanation of this with heaps of pieces. And there is some connection with more advanced mathematics. So this is the third part of the class with there is many research on fully commutative class of words in the symmetry group, or more generally in Coxeter group. Fully commutative means that if you take a class of words with a generator, we have seen the diamonds, sigma 1, sigma 2, sigma I. Then commutative class means that in the equivalence class for the symmetry group, there is only the commutation relation. You don't need the braid relation. So you have only the commutation relation, then the number of such equivalence commutative, fully commutative class is exactly the Catalan number. There's some other study in Coxeter group. There is some papers, recent papers, and all of them, you can explain everything with some heaps of dimers. Also, there is a representative theory of Lie algebra with operator on heaps, temporally Lie algebra. So this I will not, it's a whole courses. There is a book which I will now talk about. It's a minuscule, there is a book by Richard Green and his students. There are many, 3 or 4 theses around Richard Green. This is representation of Kac-Moody algebra. There is a whole book at Cambridge University Press on this, and this is representation with some operator acting on heaps. You delete a piece, so it's very deep mathematics, and also there is some extension of number theory to zeta function on the graph. So this is some active work by Giscard and Rocher nowadays, and basis of free partially commutative Lie algebra. This was a long time ago in the 90s by Lalonde, Duchamp, and many other people also. In computer science, the satisfiability problem. Donald Knuth just published in his big encyclopedia of the art of computing, he published volume 4, fascicule 6. It's about the SAT problem, and there is a main lemma by Lovac on a certain algorithm, and he said that this lemma can be proved by using the n over d, the extension, the inversion lemma on heaps. But he don't like the term heaps because heaps in computer science, it's heaps, it's a data structure, so he takes the word empilement de pièces. The French word in Knuth, not to confuse heaps of pieces with heaps as a data structure. So in computer science, there is many also many connection. In statistical physics, there is a paper on the Ising model revisited. There is a new way to prove the generating function of the Ising model by using some heaps of pieces. And now there is also a recent paper by Ram Goulang on string theory and heaps, where you have in Joe's theory. So I don't understand at all the paper, but our colleague Suresh can explain me. So you see the interest of this putting everybody under the same hat. There is 3 basic lemma: inversion lemma, logarithm lemma, and path equal heap. I put some colors, and the color correspond to, see, in each of these topics, all these 3 basic lemma appear. For example, the blue is the logarithmic lemma. In linear algebra, there is the Jacobi identity logarithm of something equal trace of exponential. Here in gas model, there is also the logarithm of the partition function, which gives the density. Here in zeta function graph, there is some formula which are explained by the logarithm. Statistical physics, Ising model is revisited. And this logarithm, you see, lemma. So for example, if I go back to these papers, then they use a Jacobi theorem. Each time they use some classical theorem mathematics, but all these theorems, even the Jacobi theorem linear algebra, they come from the same source. The same source is the logarithmic lemma on heaps. So if you go back, you see, so you put under the same roof many things where the logarithm appear. Or you see there is, so the fact that path equal heaps in green, it's everywhere, you see. Everywhere, everywhere. Yes, it's a question. Zeta function on a graph, yes. Yes, there is a book by Terrace and to extend the classical Riemann zeta function to graph. And there is different possibility, and this is very also in Giscard Rocher, they give another possible zeta function with heaps of cycle, which is more natural than the zeta function, Selberg and here was other zeta function. Well, it's a whole chapter. I will cannot explain in the first lecture. Or, it's a course of 24 hours, so you will see it. So if there is no, maybe there is no point here, you see, but from the three basic lemma plus from some elementary operation, so you can cover a lot of things. So there is some basic operator, the three basic lemma plus some basic operator, which can explain many, many things. Basic operator is like this. You add the dimers on a heap. Another basic operator is you delete what is called a maximal piece. A piece you can delete from the heap. Maximal piece means that the heap is a product of a subheap multiplied by the piece you have deleted. And another basic operator is you take any pieces inside the heap and you push it below, and what you get is a pyramid is extracted from the heap. So with this basic operator, these three basic lemma, I can do many, many things, many different applications. You don't need to know anything about physics or algebra, or I will re-explain. But this is a way to introduce to many different topics with the same basic tool and basic lemma. And the whole course also will be videotaped. There is a slide, and there is a website for the course where you can have the map of each chapter, each section, and you can go from one part of one video to another by clicking on it's like a video book. Okay, so thank you very much.